Sketching graphs. We talked a bit about relations, functions, domain, range, and so on. One of the key things was, look, if you can draw the picture, if you know what the picture looks like, a lot of these problems are a lot easier to solve, finding domain and range and so on. So let's just talk a bit about sketching graphs and the things we should be looking for and basic ideas that you've seen for quite some time now. But your axes should be evenly spaced. I mean, you have a regular axis. In other words, make sure your scale is okay. That doesn't, of course, mean that your scale on your y-axis has to be the same as your scale on your x-axis. There really is only one situation that I can think of where it would be important that the scale is the same. When would that be? Think about it. Of all the graphs that you draw, when would it be important that the scale on the y-axis was actually the same as the scale on the x-axis? Circle, yeah. If you're drawing a circle, otherwise your circle will become an ellipse or something like that. Obvious things, y-intercepts are always easy to find. That's when x equals 0. X-intercepts, well, that's when y equals 0. Not always as easy to find, and to be honest, I only bother finding them if they are easy. If they're not easy, then I don't get overly obsessed about them. Now, once you've found your intercepts, if you know the basic shape, then a rough sketch is pretty easy to draw. Okay? Never forget your basic idea. Whether you physically draw up a table of values or just substitute numbers in, way back to year 7 or what have you, and if you're unsure what a graph looks like, well, plot some points, for goodness sake, and get a feel for what the shape's doing. Right, the basics. The very most basic of them all, straight line. There's, I guess, the most basic of the straight lines, y equals x. If for some insane reason you didn't recognise it, it's a linear function, of course, y equals mx plus b. You'd notice, you go, oh look, y is to the power of 1, and over on the other side, x is to the power of 1. This must be a straight line. Okay, so I suppose that's how you would recognise the linear function. We then moved on to parabolas, the quadratic function. The most basic one, y equals x squared. We usually generalise it, ax squared plus bx plus c. Again, how we notice it is, oh look, on one side I've got a pronumerator to the power of 1. On the other side, the highest power is 2. I've probably got a parabola. Things with parabolas, x-intercepts usually are easy to find because we're just solving the quadratic, ax squared plus bx plus c equals 0. The vertex, it's a lovely symmetric shape. So once you've found those x-intercepts, you know that the axis of symmetry is going to be in the middle of those two. And so the vertex is usually easy to find as well. That's pretty much all you need with a parabola. Once you know where the vertex is and those intercepts, you can draw a nice curve. So let's do an example one. X squared minus 4x plus 3. I'm going to do it by completing the square. I find that nice and easy because then it tells me the vertex straight away. X minus 2 all squared minus 1. So I've shifted it across 2 and down 1. The vertex is 2, negative 1. X-intercepts, I would solve it. Well, as I've already completed the square, I'll keep going that way. So x minus 2 squared must equal 1. I get 1 and 3. So they're the two x-intercepts. So plot those points. I've got 1, I've got 3, I've got a vertex. Whee, there we go. I didn't even bother with the y-intercept. How's my scale? I'm just looking at where my y-intercept's gone compared to where my vertex is. 3. Oh, okay, remember a consistent scale on the y-axis is very important. Oops. Okay. We then move to the cubic. Now a cubic's an interesting shape. It's a very terribly drawn cubic, but it's very hard to draw a cubic. I don't know if you've ever tried to draw one in PowerPoint. Not easy to do. So that's meant to be the basic curve y equals x cubed, but of course that is if it can factorise to be a perfect cube. It will look like that. So ax cubed plus bx squared plus cx plus d, the most basic of them. Again, how do you recognise it? Oh look, the power's 3. Must be a cubic. Okay. But as I say, they will look like that if it can be factorised to be a perfect cube or a multiple of a perfect cube. Otherwise, it's your classic up and down. There we go. So something like that with 2 turning points. Something like that. So the other cubics will look that way. Okay, higher powers. Anything with an even power, and I'm talking about the basic one when it's factorised, will have that U sort of shape. Now, only x squared is the parabola, but they'll all have the U shape. But what you find is as the powers get bigger, the shape gets flatter at the base, steeper at the sides. And a similar thing happens with odd powers. They'll all have that what's called an inflecting shape, but the higher the power, right? So as the power gets bigger, flatter at the base, steeper at the sides. And of course polynomials can go up and down, up and down. We do a whole topic on polynomials later, and you probably might remember some from previous years. Okay, hyperbola is probably the next most basic shape that we look at. And there's y equals 1 on x. Could also be xy equals 1 or x equals 1 over y. There's all different ways of writing it. How do you recognise it? Well, look, hey, one of the pronumerals is on the top of a fraction and one's on the bottom. That usually means you've got some sort of hyperbolic shape. Another way of picking it is if the two pronumerals are multiplied together. You see an xy and you think, something's happening here. Circle, so x squared plus y squared is equal to the radius squared. How do we recognise that one? Well, now both pronumerals are to the power of 2, but the other key thing is the coefficients are the same. Now in this case the coefficients are both 1. If the coefficients were different, say I had x squared plus 2y squared, I wouldn't have a circle, it would turn into an ellipse. Now, if they were different in sign, I wouldn't have a circle, I wouldn't have an ellipse, it turns out to be a hyperbola, yeah. But really, those, what we call the conics, shapes known as the conics, most of those we don't look at until extension 2. We really just look at the basic circle, hyperbola and so on. Alright, exponentials. Exponentials, lovely graphs. There's y equals a to the power of x. Always has a y-intercept of 1 because of a to the power of 0 is always equal to 1. That is the graph if the base is bigger than 1, of course. So y equals a to the power of x. How do you recognise it? Oh, look, x is in the power. That's how we know we've got some sort of exponential graph, because another name for power is index, but then there's another name, exponent. Exponent, hence the name exponential. If a was in between 0 and 1, then you would see the reflection of that red curve in the y-axis. So if the base was in between 0 and 1, then it would flip. And of course you don't have negative bases, doesn't make sense. You don't have 0 as a base and you don't have 1 as a base. Okay, roots. Roots, I guess, can be thought of as half curves. So like the classic one is the semicircle, here, half of a circle. That one's the top half because it's the positive square root. If it was underneath, it'd be the negative square root. But you could have half of a parabola. So there's a parabola on its side, that would be y equals the square root of x. So roots usually create half of a curve. If you're unsure, then just square both sides. So, gosh, not sure, y equals the square root of r squared minus x squared. If I square both sides, oh look, x squared plus y squared equals r squared. Oh, it's a circle, but it's only the top half of it. You can do the same with the parabola. Y equals square root of x. Ooh, not sure. Square both sides, oh, y squared equals x. Ah, it's a parabola. Positive square root, top half. Negative square root, bottom half. Okay, that'll do us for today. Have some fun playing with your basic curves.